Okay, so in today's lecture, we'll discuss chapter 7, which is about capacitors and inductors. To begin, let us look at actually a circuit with only resistors and independent sources. So there is some big circuit. I'm not planning to solve this, but we'll ask a question about this circuit. So let us say we've solved this circuit and found all the currents and voltages, and specifically the current in this 7 ohm resistor. And then let us say that this 2 ampere current source suddenly is changed to 4 amperes. Very suddenly, almost instantaneously, the current changes from 2 amperes to 4 amperes. So of course all the currents and voltages in the circuit will change, and so the current in this 7 ohm resistor will change. The question is, if the 2 amp becomes 4 amps instantaneously, will the current in this 7 ohm resistor change instantaneously, or will it take time? The answer is it will change instantaneously, because currents and voltages in circuits that have only resistances and independent sources change instantaneously whenever any of the quantities in the circuits changes instantaneously. All right. So this is a fundamental property of resistive circuits. What happens if there are capacitors and or inductors in the circuit? Then when some voltage or current changes instantaneously, the currents and voltages in the rest of the circuit will take time to change. I assume you know this already from your 11th and 12th electricity studies. But we are going to study this systematically and in some detail in the next three chapters actually, chapters 7, 8, 9. Well, to some extent 10 also. Alright, so capacitors and inductors cause time dependent behaviors in circuits. Alright, so even if changes are instantaneous, currents and voltages become time dependent. So let us start looking at the simplest possible, one of the simplest possible circuits. So we have a capacitor, it's a 10 microfarad capacitor, and there is a current source, and then there is a switch. So now we'll encounter a lot of switches. So this switch is connected to ground for t less than 0, and at t equal to 0 this switch is moved from this position to this position. All right. So for t less than 0, the current source is simply connected to ground, and the current circulates from the current source into ground, and this capacitor is open circuited. At t equal to 0, this switch is moved to this position. I will assume that this switch moves from this position to this position also instantaneously for a different reason. We'll assume that it does that instantaneously because suppose this switch took time to, let's say the switch is here and it moves like this, pointer is moving like this, slowly it's moving. Then what happens to the voltage as this node when the switch is neither connected here nor connected here? What will happen if this switch is slowly moving? So the switch is here at some instant of time. What is the voltage at this node? What will be the voltage? The voltage actually will become infinite, because then we have a current source connected to nothing. And when the current source is connected to nothing, it causes infinite voltages, as we have seen before. So we don't want this switch to be floating neither here nor there for any finite amount of time. All right, but that is just an idealization. That's really not our concern for this question or this circuit. The question we are asking is that when the switch is moved to this position, so basically this is there is a connection from here to here, the voltage across the capacitor will change as a function of time. And the question I am asking is, will the voltage the mathematical form of the voltage, will it be exponential, quadratic, sinusoidal, or linear? So I'd like you to pause this video for a minute, take a pen and paper, or just think about it and see what you think this V of t will look like. Okay, take a minute or whatever. I am going to continue. Okay, so so here is the circuit. So how do we find the voltage? The way we find the voltage, we say, well, how does the current vary in a capacitor with respect to voltage? And we already have seen this equation. So this is the defining equation for a capacitor. I is equal to C dV dt, where I is the current flowing in the capacitor. So now when this switch is moved to this position, the current flowing in the capacitor, of course, is 2 amperes, because in one loop the 2 amp flows through the flows into the capacitor. So we say I is equal to C dV dt, and so we take the C on the other side, so we get dV dt equal to I by C. We do this because we know I and we want to find V. I is 2 amperes. So 2 amperes, C is 10 microfarad. So 2 amp by 10 micro is 2 times 10 raised to 5 amps per farad. And you please convince yourself that amps per farad is the same as volt per second. Okay, please do this at home. I mean on your own. You are always at home, sorry. But do it on your own time. So we get dV by dt is basically a constant. dV by dt is a constant. So what will V look like? If the derivative is a constant, V will be a linear function of time. Alright, so if you integrate both sides from time t equal to 0 to t, the voltage at t equal to 0 to the voltage V at time t. So you'll get V of t equal to 2 times 10 raised to 5 t plus V at t equal to 0. Alright, the voltage at t equal to 0. So the voltage varies linearly with time. Alright. I think in the past you have always seen capacitor voltages varying exponentially. And that is why I like to start with this example, that if a constant current supplies a capacitor, then the capacitor voltage varies linearly with time. Alright, capacitor voltages will vary in different ways depending on how they are connected in a circuit. For a constant current source, they vary linearly. They will vary exponentially when there is a resistance in the circuit, which we will see next, which is what, well, which we'll see in the next chapter actually, which we will not see right now. Not in this lecture, in the next lecture. Alright, so please remember, don't assume that capacitor voltages will always vary exponentially with time. Okay, that's one thing. The other thing is there is this V at t equal to 0. So what is happening here is that switch is moved to this position at t equal to 0. So for t less than 0, there was some voltage on the capacitor. There could have been a voltage on the capacitor. We are not even told. I did not tell you. But we assume that there may have been a voltage, and we call that voltage as V at t equal to 0. And then the voltage increases as a function of time according to this equation. Of course, it is increasing because we are providing a positive, well, a positive current is flowing into the positive terminal of the capacitor plate. Alright, so the voltage is increasing with time. But the point I want to make is that when the switch was not connected to the capacitor, there was a voltage, and that voltage could have been there forever. Alright, once a voltage is put on a capacitor, and if that capacitor is open circuited, that means there is no closed circuit, only one terminal is connected to ground, the other terminal is open, nothing is connected to it, then that capacitor will hold whatever voltage was on it forever. Alright, that is a property of a capacitor. Of course, that's a property of an ideal capacitor. Real capacitors are often leaky. There is always some leakage path. So the dielectric between the two plates may be leaking slightly, in which case the charge will leak slowly away from the positive to the negative, and it will over a period of time disappear. But that is a real capacitor. An ideal capacitor does not leak charge, and it will store the charge forever. An excellent example of a real capacitor that stores a charge for a very long time is your pen drive. The pen drive, uh, in the pen drive, so of course pen drive stores digital information, and so every bit of information, a 0 or a 1, is stored in a very special kind of a device called a floating gate MOSFET. The fundamental storing element in that floating gate MOSFET is a capacitor. So it is two plates separated by a dielectric, and if there is charge on that capacitor, then you say that it is storing a 1. If there is no charge on the capacitor, you say that it is storing a charge 0. Alright, and as you know, if you put any information on your pen drive, you store a file or a movie or a song on a pen drive, it basically gets stored as all zeros and ones over as millions of capacitors, each bit on a single capacitor. And let us say I put a song or a movie on my pen drive, and I forget about that pen drive, and it goes into hiding, and after a year I discover it, and I put the pen drive in my laptop, and that song is still there, that movie is still there. All those bits of information have been stored on capacitors. There is no voltage, there is no battery, nothing. The capacitor stores the voltage for a very long time. Right? That is the beauty of the pen drive. Of course, it doesn't store it forever. Maybe if I lost my pen drive for 5 years and I put it back, there is a probability that it would have forgotten all that was stored on it. But 1 year, 2 years is very reasonable, and that is a very long time as far as we are concerned. All right. Okay, now this is a very important question. So here is a circuit, and let us assume, so the switch is open for t less than 0 and it is closed at t equal to 0. Let us assume that when the switch was open, the capacitor voltage was 0. Alright, so in fact, let's say, it was 0 here. VC was 0, and then the switch is closed at t equal to 0. So if the switch is closed at t equal to 0, then of course this is just a wire, and so the capacitor voltage becomes equal to this DC voltage source. So the DC voltage source has a value V0. So the capacitor voltage at t equal to 0 becomes V0. Alright, so this is a plot of the capacitor voltage as a function of time. It was 0 for t less than 0. It has become V0 for t greater than 0. The question is, what is the current flowing in this circuit? Alright, that is a question. So here we can see for t less than 0, the switch was open, no current was flowing. So the current was 0 for t less than 0. If you look here, the voltage across the capacitor is constant. If the voltage is constant, the current is 0. Alright, what about at t equal to 0? That is a question. What is the current flowing in this circuit at t equal to 0? Alright, so let's answer this question by doing a bit of calculus. So we say, let this be our circuit, and let the voltage of the voltage source be given. So let me start by this black line. Let us say that the voltage applied to this capacitor is 0, and then it increases linearly with time up to some time t0, and then it becomes constant at V0. Alright, so let us say this is the voltage as a function of time, and what would be the current? Alright, what would be the current? The current, of course, will be 0 for t less than 0. So this is the current, and the black line is the current corresponding to this black line of the voltage. So the current is constant and then it becomes 0. What is the magnitude of the current? The magnitude is, we find from our equation, the current is I C dV dt. The slope of the line is, the slope of this line is V0 divided by T0, the y axis divided by the x axis, so V0 by T0. So that is the slope. All right, so this is this is the magnitude of the current. Now we ask the question, what happens as T0 is made smaller and smaller and smaller? All right, so here is a blue plot where T0 has been made smaller. So if T0 is smaller, but the voltage is going from the 0 to the same value V0, but in a smaller time. So V0 is the same, C is the same, T0 is smaller, so the current becomes larger. This blue has a larger current. If the time is made even smaller, the brown plot, then the current has to be even larger. All right, because T0 is becoming smaller, the current has to become larger. Now let's think about this physically. What is happening? We are saying the voltage across the capacitor goes from 0 to some value V0. All right, which means that a charge equal to Q equal to C times V0 must be supplied to the capacitor. Initially the charge was 0, finally the charge is CV0. That charge has to be supplied to the capacitor, this CV0, in a certain time. We are saying if I reduce the time in which the charge must be supplied, then of course I must supply a larger current, because the charge supplied is the same. In a shorter time, current must be larger to supply that same charge. All right, what happens if T0 tends to infinity? That is a question. So that is our red, which is what we had in our previous slide. So here the voltage is changing instantaneously. The voltage is changing instantaneously. T0 tends to 0. The voltage is changing in 0 time. How much is the current? Well, the answer is from calculus. If T0 tends to infinity, the current must tend, if T0 tends to 0, the current must tend to infinity. All right. So if the voltage across a capacitor changes instantaneously, what that means is that we are supplying it a finite amount of charge CV0 in 0 time. And if a finite amount of charge has to be supplied in 0 time, an infinite current must flow. All right. Okay. So this function, the function which is the I, which is 0 for t less than 0, 0 for t greater than 0, but it is infinity at t equal to 0, is called the Dirac delta function. This is a mathematical function that appears in many different physical systems. So one of these is this capacitor. All right. So so another way of saying this is that the derivative of an ideal voltage step is the Dirac delta function. Okay, so let me go back here. So we were asking this question. So this is the voltage. What is the derivative of this function? So this is, by the way, this is called a step function, an ideal step function. And the derivative of an ideal step function is the Dirac delta function, which is a function that is infinite at t equal to 0 and 0 everywhere else. All right. Okay. Now, of course, in real systems, real voltage sources cannot supply infinite currents. All right. And because real voltage sources cannot supply infinite currents, what that means is that in real systems, capacitor voltages will not change instantaneously. All right. This is a very, very important principle and a fact that we must always remember. In circuits, and we'll kind of make a broad sweeping statement that in circuits, when so let's say here, when switch is closed or open, all right, capacitor voltages will not change instantaneously, because if they do, they require infinite currents, and real voltage sources will not supply infinite currents. All right, so for example, here what will happen is, if we close the switch, then the internal resistance of the voltage source will kick in, and because of it, the current will not become infinite. All right, so this is a kind of statement that we will always keep in mind when dealing with capacitors, when, as we'll see in a minute, also inductors. All right, capacitor voltages do not change instantaneously, especially when switches are opened or closed. Okay, here is a very brief description of inductors. I think you've come across inductors again in physics. So I'm just going to do a very quick introduction to inductors, and that will be it. So let us say we have an inductor connected to some circuit. It doesn't matter what circuit it is. And we are told that because of this circuit, the current I, as I have shown, is increasing in the inductor. All right. The current I is increasing, and whenever a current is changing in an inductor, you know from, I think, Lenz's law, right? Or Faraday's law. One of those laws, I never remember which one. I think it is Lenz's law that says that whenever one tries to change the current in an inductor, it induces an EMF that opposes that change. All right. And the mathematics of this is that induced EMF is given by minus d phi dt, where phi is the flux enclosed by the inductor, and the phi can be written as L times I, where L is the inductance of the coil and I is the current flowing through the coil. And we'll assume that L is a constant, so we get E equal to minus L di by dt. Now this is physics. Okay, this is what physicists do. What electrical engineers do is say, well, I will define the voltage V across the inductor as minus E. All right, and if you think about it and apply your Lenz's law, you will come to the conclusion that the polarity of V is this. All right, so the polarity of E is the opposite of this. Okay, and so I'm leaving that to you as homework. I'm just telling you that V therefore is equal to L di by dt. All right, and this is the defining equation for us circuit people. All right, so just the way as for a capacitor, I is equal to C dV dt, for the inductor V is equal to L di by dt with these polarities. All right, remember the positive terminal is this one and the current is flowing into the positive terminal, then V is L di by dt. All right, so this defines the mathematical description of the inductor. Now because of this definition, if you apply that same principle we just did for capacitors, we say that in an inductor, current cannot change instantaneously, because if current were to change instantaneously, it would require the development of an infinite voltage, and infinite voltages are not possible. Therefore, currents will not change instantaneously in an inductor. All right, so these two fundamental principles we will remember forever. Capacitor voltages do not change instantaneously. Inductor currents do not change instantaneously. All right. Therefore, we make this statement which we will use in all subsequent, in fact, when we do the next chapter in the next lecture. So let me just read this. So if in any circuit a switch is suddenly opened or closed, all right, so we had that simple example. If a switch is opened or closed suddenly, then the voltage across any capacitor and the current in any inductor in that circuit will not change from just before to just after the opening or closing of the switch. Okay, because a switch closed or opened suddenly, but that sudden change will not allow capacitor voltages and inductor currents to change instantaneously. Okay, what that means is that we can always say that when a switch opens or closes at t equal to 0, then the capacitor voltage just before the switch closed and the capacitor voltage just after the switch closed will be equal, because it cannot change. If it had changed, it will require infinite currents, and that's not possible. And similarly for inductor currents. So incidentally, this is the kind of symbol we'll use. So when we say 0 minus, it indicates an instant just before t equal to 0, and 0 plus indicates the instant just after t equal to 0. Alright, this is a mathematical abstraction. Just after is just, it's an abstraction. Alright, just before, just after. There is no time lag from here to here. So that is why it's an abstraction. All right. Okay. So I'm going to talk about something else very quickly, which at some point I wanted to do. So I'm doing it now. So I'm just going to show you some pictures of practical resistors and capacitors, in fact, specifically. I don't know if you will do this in the lab with Professor Madhav, but I have these slides, so I'm showing them to you. So these are pictures of resistors, all right. The D I'm not worried about. So these are the resistors you'll see in the electronics lab. I think you probably have received some in the mail for Professor Madhav Rao's lab. So these are resistors, and as you probably know, these resistors are of different values. All right, they can vary from 10 ohms to 1 mega ohm, or even 5 to 10 mega ohms. All of these. These are also resistors. So what is different between these resistors and these resistors? As I said, these resistors or these resistors, all of these resistors can have values from 10 ohms to a very large value, say 1 mega ohm or so. So why would one want, or why would one have resistors that are of different physical sizes? Because clearly different values don't seem to require different sizes. So why would one make resistors that are much larger? So for it is possible that this resistor is 1 kilo ohm, and so is this, and so is this, and so is this. So these are all possibly 1 kilo ohm resistors, but they are all made of different sizes. So why would one make resistors of different sizes? The answer has to do with power dissipation. A larger sized, physically larger resistor has the capacity to dissipate a larger amount of heat. Alright, a smaller resistor will dissipate a small amount of heat. So for example, let's say this one and this one, both are 1 kilo ohm, but the amount of current that this resistor can carry will be much smaller than the amount of current that this resistor can carry. The I squared R capacity of this resistor is much larger than the I squared R capacity of this resistor. Alright, so different size resistors indicate different current carrying capacity and therefore power dissipation capacity. Alright, in fact, more fundamentally, power dissipation capacity. This can dissipate much more power. If you try to pass, if for example, if you try to pass a current through this resistor that generates a power of, let's say, 1 watt, all right, or say 3, let's say 3-4 watts, then this resistor will simply burn. Some fumes will come out and it will burn, and it will of course become an open circuit very quickly. This resistor probably can carry about 2 watts. This can carry many tens of watts. Alright, so depending on the application, one would use different sized resistors. Okay, so here is a kind of the standard resistors, these are the capacities. So the resistors you use in the lab are either quarter watt or half watt. This is slightly bigger, these are slightly bigger, they are all 2 watt. So these two are this one. This is half watt, this is 1 watt. Alright, these are many watts. Okay. Alright. These are capacitors, so different sizes. Capacitors actually do have a correlation with size, but also not. So for example, electrolytic capacitors, so some of, I think all of these, so from this yellow, this blue, this orange, they are all electrolytic capacitors. And electrolytic capacitors can give you larger values, but they are small in size. All right. If I want the same, let's say 3300 microfarad in a non-electrolytic version, then that will be much larger in size. So there is some correlation between size and the value, but at the same time, so for example, these two capacitors, you can see they can operate up to 200 volts. This is 200 volts, this is 160 volts, this is only 10 volts. So size of a capacitor also has to do with the voltage that it can withstand. So there are two things. One is the value as well as the voltage. All right. So for example, this is only 25 volt, but it is a very large capacitor. 45,000 millifarad this is. So this is 45 farads. So it's a large capacitor, but it can work only up to 25 volts. So both voltage and value determine the size of the capacitor. Okay. Now these are 60,000 volts, all right, and 50,000 amperes. So here size has to do with capacity to withstand voltages and current. So if you want large voltages, then you have to build large sizes. If they are small sizes, what will happen is a capacitor, of course, is a two metal plates separated by a dielectric, and at such large voltages, the dielectric would simply break down and become a short circuit. So unless it has made thick enough to withstand the very large voltages. Incidentally, so this structure, this ringed structure, if you are interested, please look up what this is. Why these capacitors have these ring structure. In fact, if you are walking along a road and if you look at the electrical lines by the roadside, you know, the 220 volt power lines, you will see these ring structures all over the place. At every electrical pole, you'll see them. If you are interested, please look up as to what purpose these serve. Okay. All right. So this is an internal structure of an electrolytic capacitor. It is interesting to know that if you could open up these capacitors, what you'll see inside is actually a spiral. So you have two metal plates. So this blue is the metal plate, and the whatever this yellow, brown, orangish thing is a dielectric. And this dielectric is typically some cloth material. And this metal is, of course, also it's a very thin foil of metal, and so they are flexible. So what you do is you make a spiral, so it goes round and round and round and round and round, so that a very large area, effective area of the capacitance is contained in a very small volume. All right, so this is how the internal structure of an electrolytic capacitor looks like. All right. Okay, so this is this lecture. We'll start chapter 8 next time, which is RL and RC circuits.